Let us pick one of the previously mentioned equivalencies and give a rigorous proof. Namely, let's prove that for any CTL formula phi, we have that there exists always for all always phi is equivalent to for all always phi. By the definition of formula equivalence, what we need to do is take any LTS M and state S0 in it, and show that M in S0 satisfies one if and only if it satisfies the other. To make progress, we rewrite these two statements by applying the semantics of the CTL connectives. In other words, using the corresponding cases in the inductive definition of the satisfaction relation. So the statement that M in S0 satisfies there exists always for all always phi means, by the semantics of there exists always, that we have some path pi of the form S0, S1, and so on, such that M in S0 in Si satisfies for all always phi. So we started by applying the definition of the top connective, which is there exists always, and we continue with the remaining connective, which is for all always. Note that the latter will be evaluated in the new current state, which is now Si. So after the evaluation of there exists always, the current state, which was S0, has been pushed to a new current state, which is Si, and this is the context when we evaluate the next connective for all always. The semantics of for all always tells us that for all paths starting from Si, say pi prime of the form S0, S1, S0 prime, S1 prime, and so on, M satisfies phi in each of the states S prime J of this path. And we stop here, because there's nothing else to do in terms of evaluating the semantics. We've reached the notion of satisfaction of the formula phi, about which we don't have any further information. Next, we do the same thing for the other statement, shown in blue. Namely, we rewrite it by applying the definition of the semantics. The statement says, by the semantics of for all always, that M satisfies phi in all states of all paths starting from our initial state S0. And we stop here, since we had only one connective to evaluate in this case. This concludes the routine part of the proof, just applying the definition of the satisfaction relation to decompose statements of satisfaction that involve temporal connectives. And we have rewritten our original statements into the statements 1 and 2 shown here. Now comes the creative part, which in this case is fortunately quite simple. We must prove that these two decomposed statements, 1 and 2, are equivalent. This part does not require any knowledge about the CTL connectives, but only deals with the paths in a label transition system. So we need to prove that 1 and 2 are equivalent, meaning that each one implies the other. Let's first assume 1 and aim to prove 2. Proving 2 means proving something for all paths pi starting in S0 and all positions I on those paths. Let's take such a path, and to avoid a clash of notation with the statement 1, let's call it pi prime rather than pi. And let's say its states are S0 prime, S1 prime, and so on. Note that we do not assume that pi prime starts in S0. We still assume that pi prime starts in S0. So I have that S0 prime is the same as S0. Now, let's take a position on that path that we call J rather than I. So what we must prove is that M in state S prime J satisfies phi. Let me open a parenthesis here. Renaming things to avoid name clashes happens quite often when doing proofs. Of course, changing the name does not change the property. For example, our property 2, shown in blue, is the same, stays the same if we change the universally quantified pi and the universally quantified I into pi prime and j, respectively. So we just changed the name. We did not change the property. Such renamings are usually done silently when doing proofs. End of parenthesis. Moving on, it's time to apply what we know. We know that 1 holds, which gives us a path pi starting in S0 of the form S0, S1, and so on, having the property indicated there at point 1, namely that for all positions I and all paths pi prime starting in Si and all positions j, M satisfies phi in the j state of this new path, which is S prime j. This inner part of property 1 is a for all property, so we can invoke it with any choice of the items in the for all quantification. So we take I to be 0, pi prime to be our above path, which you already named pi prime, and j to be our above position, which was already called j. So using property 1 with these instances, we get what we want, which is M in state S prime j satisfies phi. Let's visualize what we've done in this proof. Say that this is the tree of our LTS M, and we know 1. To show property 2, let pi prime be a path such as this one, for instance, and let S prime j, let's say here, be some state on it. And we want phi to hold there in S prime j. On the other hand, property 1 gives us some path pi, let's say this one, such that for all positions on it, including the first position, and any other path branching from there, including this one, pi prime, phi holds for any position on it. So it holds here as well. This shows why 1 implies 2. Now let's prove the converse, namely assume 2 and prove 1. Take pi to be any path starting in S0. Such a path is possible because we know that each state in an LTS is required to have a next state. This is by the definition of LTSs. So let's prove that this path pi does the job for ensuring property 1. What we need to show for this is that for all positions I on this path pi, and all paths pi prime starting from the ith state of pi, and all positions j on pi prime, M in state S prime j satisfies phi. To show this, we apply property 2 for the path, call it pi double prime, that consists of the ith prefix of pi followed by the ith suffix of pi prime. So our new path, pi double prime, starts as pi, and from the ith position continues as pi prime. Applying property 2 to this path gives us pi prime gives us applying property 2 to this path pi double prime gives us what we want. Namely, we know that phi holds on all, thanks to property 2, we know that phi holds on all its states, all the states of pi prime, including the I plus j state on pi prime, which is also the j state of pi prime. So we obtain that M in state S prime j satisfies phi, which is what we wanted. Let's again visualize how the proof went on our unwinding tree for the LTS M. So we know 2, and we need to show 1, which means coming up with some path pi that satisfies the property indicated here at 1. As it turns out, we can take any path. Say this one. And what we want to show is that phi holds on any path pi prime, say this one, branching from any position on pi. So say we have this path pi prime that starts from, in this example, from the second position of pi. Now, to show this, we apply property 2, which tells us that phi holds on any path starting from S0, including this one, that starts as a pi and continue as a pi prime. So this is the path pi double prime that we construct in our proof, which gives us what we wanted, because we know that phi holds on any state on pi double prime, in particular holds on any state in pi prime. This shows why 2 implies 1. Okay. Now our proof of equivalence of the two CTL formulas, namely there exists always for all always phi and for all always phi, is done. I hope you now see how you can reason about paths in LTSs to prove formula equivalences. First, you routinely expand the definition of the semantics for each connective in the statement, and then you analyze what the resulting properties say about paths in the LTS, determining that they say the same thing. The two properties say the same thing. A note here, incidentally, this particular equivalence that we proved was especially simple. It is not hard to see that both formulas say that phi holds on all states of the LTS that are reachable from S0. So in this particular case, we could avoid reasoning about paths explicitly by using instead some properties of the reachability relation. However, I purposely avoided doing that ad hoc trick because this is not possible in other cases. And I wanted to give you an idea on how to reason about actual paths, which is usually necessary when reasoning about CTL semantics.